Want to go through the review?
Mm-hmm.
Okay, we can do that. Okay, I do want you, and I have chapter, just in case I need to, I'm gonna refer to the chapter.
The slides.
Yeah.
Okay.
This is actually the first thing. What's the difference between, the types of energy? And I think it's easy because there's energy that is stored in your body. When you eat something, when you eat food, and it's stored away in your body, it's potential energy. It's not energy that you're using. It's energy that's stored, so it's potential energy. And then and then there is so-called kinetic energy. That's the energy that you're actually utilizing. Okay, so that's all that is. And by definition, in science, energy, and biology, the energy by definition is anything that is able to perform work for your body, to do something for you. So it's a very simple definition, the ability to do work. I want you to know the difference between endergonic and exergonic. Okay, for the exergonic and exergonic energy, exergonic is the ability to generate free energy for yourselves. It's energy in surplus. An exergonic equation, and I can't draw on this, but this is notes. Okay, an exergonic equation is an equation that will generate energy. So you have energy generated, like the cellular respiration equation. And I wish that I could use a pen on here. Let me see if I have a pen. Print. No. Okay. This is make a web note. No. Okay. But it is, and maybe I'll just show you the equation. I'll show you anytime you have an here it is right here. This is an example of an exergonic reaction. An exergonic reaction is this reaction right here. Let me pull this down a little bit. Let me pull it down just a little bit. An exergonic reaction, exergonic catabolic reaction is a reaction that is going to generate energy for you. And I told you in class the best way to determine that is look at the direction of the arrow. If it's big over here, a big equation over here and a small equation over here, that means that these bonds are going to be broken and energy is going to be generated from that process. So by definition, this is an exergonic catabolic energy generating process. It's going to generate energy for you. The opposite of that is an anabolic reaction, which is photosynthesis is an example of that. And the easy way to tell that is the direction of the arrow is going on this direction. You have one carbon over here, and I'm just using carbon as an example, and you have 6 carbons over here, which means that you only have, this is bond energy. This is bond energy. You have very little bond energy here. You've got a lot of bond energy right here. But the problem is that you're going to have to generate energy in order to make that. So by definition, this is an anabolic reaction. It's an energy consuming reaction because it's going to take energy to add those bonds. Okay? So that's the difference between here and here. When you eat, this is the equation for you generating, processing the food that you eat, getting energy from it. And this is photosynthesis, which uses light energy to drive the process. So there's light on this side. And I want you to kind of know the difference between this equation and this equation. Just, you don't have to know all the, 6 oxygens, 6 carbons, all of that. But I want you to understand, that it's 1 carbon over here, 6 carbons over here, 6 carbons over here, it's 1 carbon over here. And it's the reverse of the equation. It's not the reverse of the process, because, it's different here. We're not plants. But that's it. So that, by definition, that's the second. The laws of thermodynamics. the first law of thermodynamics, energy can neither be created or destroyed. It can be transformed. And in class, I used as an example a donut. On the outside of the body, you got the donut, that greasy donut, and then when you start putting it in your mouth, you start chewing it. By the time it gets down to your intestine, it's starting to break bonds. So it's actually being transformed from a greasy donut to actually bond energy, ultimately bond energy. So that the first law of thermodynamics, know it when you see it. It says that energy, you can't create it. You can change it from one form to the next, but you can't create it and you can't destroy it. Even with the case of heat, which is really, heat is a form of energy. Even with heat, you're not really destroying it. You're just not able to capture it the way that you want, but you're not destroying it. You just, okay? You get that point? Okay, and then for the second law of thermodynamics, there's a certain amount of disorder or entropy that's generated, or disorder actually, and I use heat as an example of that disorder for the second law of thermodynamics actually. Okay, so that's just that. Okay, and that's, all right, I want you to understand that, and I'm gonna pull up some things, I'm gonna pull up examples when I get to it. I kind of, when I generated this, I kind of moved all around. I tried to make it clear that and I'm going to go to this diagram really. I like this diagram better actually. When you talk about for every equation, for every single equation, and that's that C6H12O6, all equations, like here it is right here. For every single equation, there's a certain amount of bonds associated with this equation, which means there's a specific amount of bonds, which means there's a specific amount of energy. Because you get your energy from the electrons on the outermost shell. Remember that? Okay. So anyway, so for every equation, and I told you if this equation is 10 times longer than this, if you get 10 times as much energy. Okay? That's why you get more energy from fats than you do from carbs, because they have more bonds. And so this is, the total amount of energy for that equation, that for these reactants right there's a certain amount of energy, and I'm just going to use this as my Gibbs free energy. The Gibbs free energy equation, and let me back up for 1 second, because in order to explain this, for the Gibbs free energy equation, the Gibbs gives us a way of determining how much free energy, how much available free, physicists would hate me for describing it like this, but Gibbs free energy is related to the amount of free available energy you have available in that related to that equation, and the way that the equation is, the way that it is, this is the heat measures temperature, and I'm just explaining it. The entropy and the heat, temperature, heat, and entropy. So the heat is on this side, the bond energy is right here, and then the delta G is the whenever you see, and I don't want to get through the whole thing because it might take me forever, but delta means that something has been subtracted from something else. So you want this number to be as small as possible, okay? And what that means is delta G. What that means is that you have used, this is how much you've used, and how much is available, how much is free and available for you to use for something else. So the smaller this number is, that means you've used very little. The way that this equation is formulated, you use very little, so you have a lot left over. Are you with me on that? So this delta H is the change in the bond energy. Delta means change. It's not an absolute value. It is a change. I tried to have this right here. Something was subtracted from something else. Delta means that there's a change. You want this change in, there's a total amount, maybe I should start this way. There's a total amount of bond energy associated with whatever equation you're using, right? Certain amount of bond energy. We're all on the same page, right? So H by itself is total bond energy, but delta H is a change in the bond energy, meaning you know, how much you've used. You want to use as little. Delta is the change from what you've used minus the total amount. That's what delta is. So you want that number to be as small, you want this number to be as small as possible. So if you use very little of that bond energy, then this number is going to be negative, subtracting it from this. And this number is going to be negative as well. You wanted it to be as small as possible. As small as possible just means that you have utilized, you've used very little, which means you got a lot left over. That's all that means. Are you with me? So that's the point I want you to understand about this. Some people get a little bit confused when thinking about deltas, you know, the delta value. It's not an absolute value. Delta is not an absolute value. It means it's a change in something. Whenever you see delta, it means that something has been subtracted from something else. It's not an absolute number. It's not an absolute number. Okay, so anyway, you want this number to be as small as, so if I have, and I'm just going to use as an example, I'm going to pull something out of my hat. I have 1,000 bond energy units that I started with. If I use, you know, one bond energy to do something with, then, you know, I have 9 bond energies to do something with later. Do you see the point? So that's all. You want this number to be as small as possible. And in class, I used the example that, you know, what kind of example did I use about the bond energy? You know, but anyway, let's look at this. I forgot the example will come to me in a second. Okay, now, so this is the energy, and this is free energy on this axis, on the y-axis, on the x-axis, if we can call it an x. You know, it's the reaction. So for the bond, for the free energy associated with the reactants, all this says is this C6H12O6 has this much free energy. It has this much energy associated with that process, this. And it says that to generate the product, to generate this product, which is that individual carbon, six of the carbons, but individual carbon. In order to generate those, what's on that right-hand side, I use this much energy. Are you with me so far? I have this much, but I use that much. What that means is this much is available and left over. So the free energy for here is a positive, it's positive free energy, but if I use the Gibbs free energy equation, it would be a negative number, okay? Because I've used very little, okay? So the point is that I've used very little to make this, so I have a lot of free energy left over. And the opposite is for this equation. For this equation, I have only this amount for my reactants, because it's got very few bonds. I have this much energy, but I have to use a whole bunch to generate that. Are you with me? To generate the product, which is a large molecule. I'm making bonds. To make bonds, it takes energy. When you break bonds, you get energy. You get energy from bonds. And if you got to make a whole bunch of bonds, you're going to lose a bunch of energy. Okay? All right, so anyway, so this is what this diagram shows. So it shows that I've used more than I have, which means that I had to put energy from an outside source. And in this case, and in our body, we have the same kind of equations. We don't make, you know, actually we do go through, quite frankly, we go through gluconeogenesis, which is making stuff just like this. But the point I want to make is that if you use energy to make that. Are you with me? So by definition, this is an energy consuming mechanism. It takes energy. This is an energy generating mechanism. So it defines what happens when you eat. When you eat, you always get energy. You always, an energy drink. That's why they call it an energy drink. Even an energy drink, everything except for water, you're gonna generate energy. Okay. Energy drink, you get a lot of energy actually, because you're breaking down something in that drink. Okay. Oh, actually, this is one of the things. I'm going to go back I'm gonna just use this since it's up, but this is one of the questions that's, one of the things that's on the, and actually it's one of the diagrams on the, hold on one second. It's one of the diagrams, it's right here. It's a diagram, so I'm just gonna go talk about it while it's already up. Excuse me. Okay, so, goodness, come back. Okay, so this actually describes what enzymes do. In all of your life, they're always going to define enzymes the very same way. Most enzymes are proteins. Most of them are proteins. 99% of them are proteins. It's going to define enzymes as a molecule that will lower, and it's on every single test you will ever take. It's going to lower the energy needed to start that process. They call it the activation energy. Here's what I want to mention about this, and I might make this as an extra credit question actually. That energy is separate from the energy associated with that equation. So here's the energy with the equation at this dotted line right here. That's the energy associated with the reactants and the products. But the enzyme, when a protein, and I'll just say a protein because enzymes are protein. When a protein sees another molecule and it's going to bind to that molecule, before it does anything, it's got to activate the process. And it's got to come in, and they call that induced fit, where it's just trying to get a perfect fit. And it really, I'm doing it like it takes a long time. It doesn't take a long time. But it's just trying to fit itself into that reactive site. Reactive site for another protein, active site for any other molecule. So it's got to go in here and do like this before it locks in and goes forward. Mm-hmm. So what this is it's that time, this time right here, from that red line down to that dash. So it's the energy, they call it the activation energy. I'll just call it to start or activate the process. Are you with me? And it is separate from the bond energy, because it has nothing. I was gonna say it has nothing, but it really is separate from the bond energy associated with that equation, which is this right here. So what the enzyme will do, it will lower and if you have 1 million reactions going on in your body, which you do, you have millions of these reactions, and if you decrease them all by a little bit, that's a huge amount. Do you see the point? So without the enzyme is that blue line. So if the enzyme was not present, it would take this much energy, and I just want to make a point. I feel like I'm going real fast. Make a point that this is different energy. I'm not talking about the energy associated with the equation, the bond energy. That's separate. That's another kind of energy. Are you with me? And so this is the energy needed to start that process. Without the enzyme, it's this. With the enzyme, it's significantly better. And if you have millions of these going on, which you do in your body, it makes a huge difference. And this is just a diagram, but that's what it means. Enzymes will lower the energy, the activation energy. And activation energy, in very simple terms, is just the energy needed to activate and start the process. Okay, and it is separate from that bond, the bond. It's just, okay, that's why they call it activation energy. It's activation, that's what it's about. Okay, now, let me just go back up here and start, and maybe you go through here. Okay, I've already talked about that. I want you to know oxidation reduction. I do. I just want you to, and I probably have this on tests that have nothing to do with oxidation reduction, because I just think it's an important terminology to understand. When something is, like, for instance, I'll use glucose as an example. Like my donut that I eat, and I'm digesting it and breaking down. When I'm literally stripping electrons, I'm stripping bonds, because that's what digestion is. It's breaking bonds, right? It's breaking bonds. So that glucose molecule gets oxidized because you're taking electrons away from it, right? It's losing electrons. So oxidation is the process of losing electrons. Reduction is the process, whoever whoever binds those electrons or captures those electrons becomes reduced. Are you with me? Reduction. Electrons are negative. Electrons are negative. They're negative. You know, very little contribution to size. You know, they're negative. And the way that I've always, when I was in high school, I might have told you the story. The way that I would remember is, when you're accepting something that is negative, that is less, you become reduced. And that's what this is. You have to find a way to kind of understand and remember these things. Okay, so anyway, so that's what reduction and oxidation is. Okay, and during the process of eating, you know, when you're stripping all those electrons from that donut, because that's exactly what you're doing, you're oxidizing those molecules. And whoever accepts it, and we have these temporary carriers, and here's the next one, you know, these temporary electron carriers or acceptors, and in class I use the term interchangeably, you know, these molecules that would temporarily accept the electrons, and actually electrons and protons really, and for us it's the NAD, for us, and it becomes NADH, and for plants it's NADP, okay? P for plants or whatever, or photosynthesis, however you want to remember it. But they're different. NAD for us becomes NADH. For plants, it's NADP, and it becomes NADPH. And it's just, they're, you know, they are temporary acceptors. Some texts call them carriers, acceptors, all the same terminology, all the same meaning. Okay, all right, now, I want you to know what cofactors are. You know, cofactors and coenzymes. When we were talking about those, there were 96, we talked about carbon, oxygen, hydrogen, nitrogen. Remember the 96% of what you are is carbon, oxygen, hydrogen, nitrogen. There was another, it's 96%, there were 4% of these other divalents, mostly divalent ions, magnesium, zinc, magnesium, zinc, those are the major ones. And they were in that 4% category. And I know you don't remember, but I told you when we get to proteins, I'm going to bring those up again. I know you don't remember, but that's what I said. Okay, but it's what, and those molecules, what those molecules will do, and I'll just make this a little bit bigger, what those, co means to cooperate. Anytime you hear the word co, it means to help. A lot of times in biology, all you have to do is break the word up and you know what it means. So co means it's a positive helper. So that means that those ions, the magnesium, the zinc, you know, they cooperate to make enzymes better. And here's what I mentioned in class, and I really think that this is the easiest way to remember all of this. Anything that when an enzyme or a molecule is bonding to another molecule, anything that makes this bonding better and tighter is good. Anything that eliminates this site and makes it so that this molecule can't bind is bad. Good, bad. Good, bad. Are you with me? And what coenzymes will do is they make this bonding tighter. They make this bonding, what they'll do in a lot of cases, I'm just going to scroll this down. I can't scroll this down. But what they'll do is they will bind to a, and since I have this up, you know, that's an inhibitor. See how the little brown thing is the molecule that's supposed to fit in that space. Mm-hmm. And the other molecule is a molecule that's not supposed to be there. It's an inhibitor. Do you see the point? So it's blocking, so, and that is how just about every single drug that's on the market works. That's how they work. That's just about how every single, now, going back to the coenzyme, with the coenzyme, if it's cooperating, then all it's going to do is help it's going to make that bonding, that little region tighter. Anything that makes that bonding interaction, that interaction good and tighter, is gonna help it work. Anything that blocks it or eliminates it, if I get out on the cold and I have, you know, my site where things are supposed to bind is eliminated, it's gonna be, it's not gonna go forward. Do you see the point? So and proteins are absolutely dependent upon having good fits, because proteins, which enzymes are proteins, all proteins are absolutely look at structure. When they're seeing who a partner is going to be, they're looking at whether or not that partner is going to fit like a puzzle, or whatever. I think the example I use, like a lock and a key in class, are like a puzzle. Okay, so anything that makes that like a cofactor could function like that little green thing right there, you know, bonding to it so that it kind of moves the shape just a little bit so that it's a tighter shape, a tighter interaction. Okay, so I don't have to go through inhibitor and inhibitor, because there are molecules that will inhibit and there are molecules that will help. Yes?
So what's a cofactor?
The cofactor is like magnesium, zinc. Those are cofactors. They're generally divalents. I forgot to mention. They're usually, yeah, they are, now they're also what they call coenzymes, you know, and that's what vitamins do, okay? But they all cooperate with, meaning to cooperate, meaning to make better, to make better. So they allow the enzyme or the molecule to work and do its best job. Are we good? Okay. All right. Now, free energy. I'm not gonna have the equation on there. I just, you know, every once in a while I throw in something on the review to have you know it. But okay, okay. Coenzymes. Okay, various factors. Induce fit. I've already talked about that induce fit to make a, you know, that's that induced fit. And I talk about it like it's slow, but it's very fast. It just, you know, but when they see each other, they do have to kind of do all this kind of wiggling before they lock in and go forward. So you can see that that's activation, and that is not related to the bond energy. The bond energy is separate. Okay, now, for this, certainly absolutely going to have this on here. So enzymes are proteins, mostly 99.9% or so are proteins. And they are very sensitive, and I don't have a diagram, they're very sensitive to anything that will eliminate this. Like say, this is my enzyme X. Anything that's going to eliminate this site or have an effect on this, that binding, they call it the active site. I'm reluctant to call it that, because when you're talking about, it could be active site or reactive site, but the site where something else is going to bind. The point is that things like temperature, pH will totally obliterate that site. So if you heat something up, and I used the example in class, I said that, you know, why do you boil water after a hurricane? Remember that? And you boil water after a hurricane because there are organisms. Somebody said, could have been one of you. You put there are microbes in that water. They contaminate the water, and you want to kill them. And the best way to kill them is to boil them and kill the proteins. And what you're doing to that protein, and I'm just using this as my example, is you're eliminating that active site. You're killing it so they can't interact with anything. So all the 40,000 proteins that are not going to have 40,000, because it's 2,000 for a microbe. They don't have as many proteins as us. Then it's going to eliminate it's going to kill the protein from all the proteins. So none of them are going to be able to work. The DNA is not going to be able to work, because the DNA is not going to be a double helix anymore. It's going to be separated into individual strands, because that's what heat does. Heat expands, and it absolutely breaks all those bonds. The ionic bonding interaction, the hydrogen bonding interaction, the van der Waals, all of those bonding interactions are necessary for this structure. And when you heat it, you get rid of all of those. And it kills the microbe. That's the best and most efficient way to do that, okay? So that is called denaturation. I wish that I'd used that word more, because I think it's a very important word, denaturation, because it's denaturing and eliminating the structure and killing it. Okay, are we good? Okay, now I'm not going to go over this last part right here because I've already gone over it. Anything that's going to now a cofactor can, you know, forget about this inhibitor thing right here, but a cofactor, you know, actually a cofactor can bond anywhere. It can bond at the active site. There are instances where it bonds at the site where this is supposed to be, but it doesn't get in the way. Mm-hmm. It's because it's cooperating. It's a co. That's what co means. Co is a positive term. And allosteric just means it's bonding to a site other than the designated active site. And it came to me that I was doing something with somebody, and we were looking at a protein molecule, and then on that protein molecule, this is just a thought that came into mind. It just happened yesterday. Oh, actually, it happened this morning in one of my senior level classes. We were looking at a protein, and when you're looking at the structure of the protein, we saw all these sites. This site, one site, two site. You know, it was a big protein, and then somebody in the one of the seniors said, "Well, I thought there was just one site for a protein." It's not. There can be 100 sites, meaning it can have 100 partners. So, but anyway, we're making it simple right here. Anything that makes this better is good. If it gets in the way and blocks, like in this particular diagram, bad. Okay, if it's an inhibitor. And most of the drugs that are on the market work like that. They use that kind of approach. They're designer drugs. They're designer drugs, actually. Okay, now let's go to chapter 7, and let me see chapter 7. And then I'm going to pull up